This lesson deals with a wideband common emitter amplifier analysis. You can find these notes in the ECE302 ebook in Chapter 10, starting on page 30. In our last video, we looked at a common emitter amplifier using a model that would cover a much higher frequency range. This is on page 24. Let's go back to that. So this was our common emitter amplifier where we had stuck in an AC model for every component. There was a battery which resulted in a short circuit here and here for the connecting parts. And then we stuck in the Giacoletto model for the BJT. And this is the circuit we need to analyze, but it's pretty complicated. Very hard to solve for the transfer functions. So we broke it into pieces, the first one being a midband analysis, where we short-circuited the big capacitors and open-circuited the little capacitors. Next, we look at low frequencies, where we open-circuited the little capacitors and left in the big ones. And we used an approximation called the short-circuit time constant method to come up with an approximate equation. Go back to page 30. Let's take a look at the high-frequency analysis of this amplifier on page 24. We're above frequencies that were called mid-band. The big capacitors are short-circuited. As the frequency increases, the smaller capacitors will eventually go from an open circuit to a short circuit. The circuit we had for the mid-band analysis is still part of what we have here, but we're going to add in the two capacitors. Same schematic, just put in the capacitors, in this case C-pi and C-mu. If we're trying to analyze this circuit and we did a source transformation, there would be 1, 2, 3 nodes. So we have a 3x3 matrix to solve. And symbolically, that's a pretty long expression. Was there a shortcut method that we could again apply that would let us solve for the high frequency corner in the overall Bode plot? And the answer is yes. It's called the open circuit time constants, or OTC for short. And you can find the derivation for this in the supplemental problems. Let me just show you how to use the algorithm. If you're trying to solve for a transfer function, say V out over V in, or this can be anywhere in your circuit, and you want to solve for the high frequency 3 dB point, we'll do the following things. We'll set V in equal to 0. If this was V sub s, we would set V sub s equal to 0. And for each small capacitor, these are things in the picofarad range, we're going to find the resistance looking into its terminals with all the remaining small capacitors open circuited. The high frequency corner in radians per second is 2 pi times the frequency in hertz. And that's now going to be 1 over the summation of these time constants. Let's apply this to our circuit and then compare it to our simulation. The first step of this algorithm is to take our circuit, which was shown on page 30, just going to repeat it right here, and we're going to set V in equal to 0 because we're going to be solving for V out over V in. Again, if we were solving for V out over V sub s, we would short V sub s. Shorting this gets rid of this part of the circuit, so I didn't show it again. Let's even simplify this up a little bit. Here I've got a short circuit in parallel with the 10K and 5K resistors, so that's just equal to 0. And then I have these three in parallel, which is the 1K and the 2K, but also this RO of 19.1K, and that's 644.2 ohms. Let's start with C-pi. Let's look in here with this one open circuited. Well, if you do that, it's really applying a voltage here and measuring a current, but the controlled source is over here and there's no connection between the two, so all we see really is this resistor in parallel with this one. Looking into this terminal, I'll call it R10, we have that that's equal to the parallel combination of 10 ohms and 1.17K. Multiply that by 52.8 picofarads, and you get 523.5 picoseconds. We're going to take this and we're going to add it to the next one, and then take the reciprocal of the summation. Let's next find the resistance looking into C-mu with C-pi open. If you were to apply a voltage here, a current would flow, creating a drop across here, which would cause this to have some value. Let's go around the loop. The rise in voltage is V test, and then the drop is going to be I test flowing into these two parallel resistors, which we said were 9.915 ohms. Rise in voltage equals that drop. And then think of this ground symbol as just one big node. That current I test enters. It comes out, but there's also this current here. So the current in here is going to be I test plus the 0.153 times V pi. And that's going to flow in the 644.2 ohm resistor. I have V test in terms of I test, in terms of I test, in terms of V pi. What's V pi in terms of either V test or I test? Well, V pi is equal to the voltage across here, and the current is I test. So 9.915 times I test is V pi. We can now put that back over here. Say the V test is equal to I test times 9.915, 644.2. Pull out the I test, there's a 1. And we have 0.153. Pull out the I test, and we have 9.915 multiplying 0.153. All of that's equal to 1.631K. We'll call that R20. The resistance looking into capacitor 2 with the other capacitor is open circuit, in this case one other capacitor. Multiply that by the capacitance of 1.86 picofarads and you get 3.034 nanoseconds. Even though that capacitor was smaller than C-pi, it has a bigger effect. Looking into the C-pi capacitor, we saw that resistance and then that product, and here a little bit bigger number. This is going to dominate the results. You get 281.1 megaradians per second. Divide that by 2 pi and we get 44.76 megahertz. We did the simulation in an earlier video and we measured 47.8 megahertz. Very close. This is an approximation, but it gives us an idea what's controlling the parameters in our analysis. Most of the circuits in my ebooks I've built and tested to make sure they do what I'm saying that they're doing. And the reason for doing this is that over the years I did the same for textbook circuits, and sometimes the circuit would be quite different than what the author had described. Making sure the stuff in this particular ebook was accurate, I built and tested the circuit on page 21, and I found that the low frequency corner was pretty much where we had simulated and likewise calculated, and the mid-band gain came out very close, again, to what we simulated and what we calculated, but the high frequency corner was way, way off. I had to think about that for a little bit, saying, well, what am I doing differently than what we did in the simulation or the hand calculations? Well, the difference was I put an oscilloscope probe in the circuit. If you go back to ECE302, we talked about equivalent circuits of a scope probe. I've shown this here. The probe that I'm actually using in my lab is an HP 1168 probe, and this is the equivalent circuit of it when hooked up to the scope. At the tip, it has a 10 picofarad in parallel with a 9 megohm, and with the scope and the back side of the probe, there's 1 megohm in parallel with 90 picofarads. Now in ECE203, we talked about balancing the probe, and when you balance the probe, and that's a product of these RC time constants equal to each other, you can take this connection and break it in the sense that you have a series combination of resistors and a series combination of capacitors at that balance condition. The series combination of resistors is 9 megohm in series with 1 megohm, it's 10 megohms, and then you have a series combination of a 10 picofarad and a 90 picofarad capacitor, and that's a product over a sum. The equivalent circuit at this tip looking in, called at Zn, is 10 megohms in parallel with 9 picofarads. Let's go put that in our circuit for high frequencies. A scope probe here at node 2, and a scope probe at node 7. Well, we're going to set this equal to 0 by short circuiting it, so this won't have any effect. Over here I have a 10 megohm in parallel with a 9 picofarad. 10 megohms in parallel with these resistances won't have much of an effect, but the 9 picofarads is of a similar size to these capacitors, so probably does have an effect. Let's see if we can figure out what it is. When I open circuit this capacitor and open circuit this capacitor, I disconnect the circuit from here. If I were to take this cap off and apply a test voltage, none of that voltage gets over to here because of this open circuit. There would be no current here and therefore no voltage for this controlled source as a product, and so it would be zero current in open circuit. All I see looking back here is a 10 megohm in parallel with the 2K, 1K, and the 19.1K. And that's still about 644.2 ohms. Multiply that by the 9 picofarads, and you get 5.8 nanoseconds. We're going to add that to our other two previous results, but this is much bigger than either of these two. We'll change the result. In fact, this turns out to be 17.02 megahertz. That's about a 2/3 loss in our bandwidth for our circuit. Let's go and do a simulation and see what happens. I went back and took the PSpice file on page 21 and added this scope probe to the input and the output. The scope probe was between nodes 2 and ground and 7 and ground. And I'm showing the balance condition where I have a 9 picofarad in parallel with a 10 megohm resistor. I run the same file, and now let's take a look at the transfer curve in dB. Here's my output over my input. You can see the mid-band gain is exactly the same, the 3 dB and the low end is the same, but the high frequency 3 dB has changed, and it's actually 17.8 megahertz. And what's causing this is very much the scope probe. Spice can find the results, it's just that why do we see particular numbers? Well, we've got these analysis techniques that allow us to approximate where this point and this point and this point are coming from. And if we want to make changes to the design or want to explain what's happening, we can use these analysis techniques to do that. And this is a wideband common emitter amplifier analysis.